Hello everyone. In this episode, I want to talk about the generators in a group and the cyclic groups. At first, let's look at the generators. The generators is an idea like this. If you have a group G, then you must have some elements in the group G. But some of the elements are very special, and you can call them the generators. And those generators have a special property that for any element in this group G, you can always use the generators or the inverse of the generators to represent this element, which means you can, if you just know the generators, you can just use the generators to construct the entire group G with the operations in the group, and that means the generators contains the entire information of the whole group. So that is why the generators are very powerful. And here this is the definition of the generators in a group. So it says this subset S, which is actually the set of generators, is the set of elements of a group G with the property that every element of G can be written as a finite product of elements of S and their inverses. If this property is true, then this set can be called as a set of generators of G. Okay, so this means for any element of a group G, and there is a subset of G, then we can write the set contains the elements S1, S2 until Sn. Okay, if those are the generators of this group, then G can be written as some, like the finite product of some elements or the inverse of those generators. So maybe G can be written as S5 times S7, maybe the inverse of S7 times S maybe 100 if n is greater than 100, like this. If every element G in the group G can be written as such a format, which is the finite product of elements from here or the inverse of those elements, then this set S is called the set of generators. Okay, let's look at an actual example. So for example, if the group is the G equals to the group of integers under addition, so this group is the group contains all the integers, and the operation in the group is the addition, and this group has a set of generator S equals to set of one element, and that element is 1, so it only have one generator for this group G, and we can verify this. So maybe let's look at some examples first. For example, for integer phi, it is the integer in the group G, and phi can be written as 1 plus 1 plus 1 plus 1 plus 1. There are 5 ones. So we can see that the integer phi can be written as a finite addition of ones, and the 1 is from this set S. Here we can see in the definition we need that every element can be written as a finite product of elements or their inverse in the S. But here the product does not necessarily mean the multiplication. It just means the operation you are using in the group. So because we are using addition in this group, so the product here just means the addition. Okay. Then we can also check the negative number, -3, and -3 actually equals to -1 plus -1 plus -1. It is the addition of 3 negative ones, but the -1 does not in the set S, but because in the definition we allow the inverse of those generators. So because -1 plus 1 equals to 0, and 0 is the identity element of the group G of integers. So -1 is the inverse of 1. So the finite addition of the inverse of 1 also a valid expression like we need in this definition. So -1 works as well. And how about 0? 0 in the integer, and 0 just equals to 0 numbers of ones. So that is still finite number of ones. So 0 it also works. So according to this idea, we can prove that every integer of n, every integer of the group can be written as a finite addition of 1 or -1. So 1 is just like the set only contains 1 is the generator set of the group G. And here, if the set S is the generator set of G, we can use this notation: E equals to the angled bracket with S to represent that the group G is generated by the generators in S, which means that every element in G can be constructed by the elements of S or the inverse elements of S. So, and in this example, it just means that G equals to the group generated by S, and this equals to the group generated by just 1. Okay, this is the idea of generators. Then we can look at the idea of cyclic groups, because the idea of cyclic groups is based on the generators. And here we can see the definition of a cyclic group. It says that a group H is cyclic if H can be generated by a single element, which is exactly like what we see in this example. We only have one generator, which is 1 for this group G. Then this group G is a cyclic group. Okay, and in general, for this group H, it is generated by something like A, one element A. Then we call this group H is the cyclic group. Okay, and this group is very interesting because it's very simple at first, and it has a lot of good property. We will use this like this idea, this concept of cyclic very often in the future. So let's look at some maybe nice property about it. At first, if we carefully look at what the number of this or what's the elements of this group, we can find that H is just equal to the power of the generators, n equals to integers, like this, just like we can see in the definition. Here it use x as the generator, but we use a. Maybe we can change it like x like this. So it means that for any element, maybe h in this cyclic group H, then H should equal to x2, we use another notation, m for some m in integer. So every element of the cyclic group is a power of the generator. So this is a very good property because it is easier for us to know the element of this group, and it is very simple and very just very easy to understand. And also there are different types of cyclic group, like for example, in this example we can see that the group G is an infinite group because it contains infinitely many elements, because the integers, there are infinitely many integers. But if the generator X has order maybe k is finite, then the group H will be a finite cyclic group, which H will be a finite group like this. It contains the elements 1, x, the generator itself, x squared, x third, and until x to k minus 1, those elements. The reason is that for 1, it means there are 0 number of x multiplied together, and the element x means there is 1 x in the like a finite product of the generators, and the x squared means the like a product of 2x, x to 3 is product of 3 generators, and until x to k minus 1. The reason we ended here is because for any, like maybe if we use consider xk, what is xk, because the order of x is k, so xk is equals to 1, so it just go back to here, it just equal to this one. And what about xk plus 1? Xk plus 1 equals to xk times x, just equal to 1 times x is equal to x, so it's this one. So for any like element with higher power than k minus 1, it's just some elements in like before the last element. So it just go repeating some elements inside this set. So this set contains all the elements of this cyclic group of the generator, if the generator X only have finite order k, and we call this like a group has the order k as well. Okay, this is the finite cyclic group. Okay, I think that's all I want to talk about in this episode, and thank you for watching. See you next time.